Welcome to numerical ship and offshore hydrodynamics. Today we are going to discuss on the forward speed effect. So, today is the lecture 36. Today we covered this following concepts, that we have discussed something called encounter frequency, and then we have to discuss something on kinematic and dynamic, how it is the kinematic and the free surface boundary condition for a moving frame of reference. Okay. And these are the keywords that you have to use to get this lecture. Okay. So, let us jump into the problem, like that something that we are going to discuss, something called the encounter frequency, and we call this as omega e, or we call the omega encounter. Now, what is encounter frequency or what is omega e? Now, suppose let me draw one just a sketch of a ship. From the top view, I am looking from the top. Now, if suppose this is not moving, this ship is not moving at all, okay, with respect to position, it is always fixed. So, let us pick a coordinate system also now. Now, this is the coordinate system of the vessel. Okay. So, let us fix x, y and z. Now, with respect to this coordinate system, the ship is not moving at all. Now, you can, and then the observer here, suppose there is some observer is standing here and he is observing that when this wave crest actually approaching to this point. Okay. So, now he observed the first wave is here, then this wave is slowly coming and hitting here, and then this time he found out that this time taken to coming this crest here and then slowly this will come. So, consecutively these two crests, this time let us say 10 seconds. So, that means the observer can see over here that each 10 second that wave is hitting to the ship, okay. And then subsequently we can understand then that frequency, or in that case the encounter frequency omega, and which is omega e, that is nothing but 2 pi by 10 second. And if you look at this, what is the wave frequency here? Now, wave frequency also remains same, because omega here also, which is 2 pi by 10. So, therefore, in this case this encounter frequency is equal to the wave frequency omega e, right. So, we have no doubt about this, like if there is the ship is standing still and it is not moving with some velocity, there that moment of time the observer, if I see the time period that wave is approaching and hitting to the ship is a 10 second, that is exactly what the wave time period. So, there is no doubt about this. Now, let us take a second situation. Now, in this time what is happening? Now, again we have the ship. Now, at t equal to 0 it is here, and then again some observer here is standing and just looking at this the whole process, and then wave is slowly coming and approaching, right. It may not be very good waves anyways. Now, what is happening, this when these waves approaching this point, by that time that ship moves little bit forward, because it is moving with some velocity v. Now, what is happening now, if is a period of 10 second, now in this case if the wave frequency or let us say this omega is equal to 2 pi by 10, or maybe this time period of the wave T p equal to 10 second. Now, for this observer, he might, I mean, he can observe that this time taken between these two consecutive waves are not 10 second, because this ship is moving forward, it could be some 8 second, let us say. So, for the observer what he can observe as follows, he observed that for him the time period is nothing but the 8 second, and consequently that encounter frequency, it is nothing but 2 pi by 8. Now, in this case you can see that omega e not equal to the wave frequency omega. Now, then the question is, then at which frequency the shift should oscillate, right. Now, here you have two questions, right. Now, you see there is omega, it is, let us say or let us say, let us try to find out t, we are much more comfortable with the time period. So, let us say t equal to 10 second, and then you can see that encounter time period is 8 second. Now, the question is about which time period or which frequency the shift should oscillate. Now, the answer is very straightforward. The answer is it should oscillate about this encounter time period or encounter frequency omega e, right. So, this is how, I mean, this is the first difference between the fixed case and then a ship advancing with some velocity v, right. Now, if the ship advancing with some velocity v, then actually this wave frequency omega is not the same because of this forward velocity v. So, ship cannot oscillate with respect to omega, it should be omega e. Now, if I try to find out the motion of this ship, then definitely let us say vertical motion z, then z should be some amplitude xi z, let us say, and then it should be the cos of omega e t, that should be the motion of the body. In other words, or if you write in complex domain, z is equal to some xi z e to the power I into omega into e into t, right. So, this is the underlying concept of the encounter frequency, right. So, now this encounter frequency, let us now quickly go to some kind of definition, which is one is angle of attack. Okay. So, now what is angle of attack? Because you see, like now you see the problem is the ship normally all the time I am not encountering the waves which is coming only on this direction. Sometimes wave might coming with some angle, like, or sometimes it can come from this other side also, this way also. So, then this angle, I mean some angle we need to define, because it always it is not coming from the front, right, not possible, because it is a 3-dimensional phenomena, wave can approach from any direction. So, therefore, I can understand this omega e may be, I mean not maybe, definitely the function of first that velocity that ship is travelling, and also that omega, that means the wave frequency. Not only that, there must be some angle between them which is called the angle of attack. Okay. So, this definitely depending on this 3 parameters, and there is always one parameter which is the depth, like we will see later. So, now first we need to define the all 3 parameters. So, we know what is v, we defined v, we defined omega. Now, we need to define what is called the beta. Now, beta is, suppose if this is the direction of the ship and if this is the direction of the wave, normally we can define this angle is my angle beta, which is started from here to here. Okay. So, with this definition, let us quickly find out that what is the angle of attack for some situation. Let us take the case 1. Now, in case 1, now let us say, now I am not drawing the ship, okay, or I can draw also. So, this is one, it is going this way and then the wave is coming this side. Then what is the beta in this case, let us say. Now, as you know, as I said that it should be from this direction to that direction. So, it definitely this is the angle. So, in this case my beta equal to 180 degree. So, I understand for head wave situation the heading angle, we can also call the heading angle or angle of attack. So, that is also is a 180 degree. Now, for let us say the follow we can call is a head waves. And second is called the following waves. Now, following waves, now this is my the ship, ship also going here this direction, and also the wave also going in the same direction. Now, then this angle is beta. Now, in this case this beta equal to 0 degree, right. So, therefore, in following C condition it is 0 degree, right. So, in that way, so this is the definition of my beta. Okay. Now, with respect to this definition, let us try to find out the relationship between the wave frequency omega and the encounter frequency omega e. Okay. Now, let us take, so let us say this is your the ship is moving with a velocity v, and let us take this wave is moving with the velocity v omega. So, definitely this is the angle beta. So, then if I call the relative velocity, or you can call the v relative or velocity encounter velocity, definitely that equal to my v omega minus v cos beta, right, fine. Now, remember one thing, that the velocity v equal to omega by k. So, that is or lambda by t, both is known to you, right. So, therefore, this v definitely we can now from v we can write this omega e by k equal to, now v omega is now it is omega by k minus v cos beta, and then if you multiply throughout the k. So, then we can get omega e equal to omega minus v into k into cos beta. This is one way you can find out. There is, I think, I mean, there is many way you can get it. So, this is one. Now, we can make alternative expression also. For example, I can take this v equal to v omega minus v into cos of beta, and then I can write v equal to omega e by k, and here I can take common v omega. So, I can get 1 minus v by v omega into cos of beta, and then I can write omega by k is equal to omega by k into 1 minus v by v omega into cos beta. So, I can cancel k. So, I can get another expression something like omega e equal to omega into 1 minus v by v omega into cos beta, right. I mean, you can take anything, right. At the end everything should be same. Now, since this omega e cannot be negative, but there is some situation you can see from here that omega e can be negative, right. So, normally when you do the mathematics, or when you solve it, normally we try to take the normally we take the modulus of it. So, that to make sure that encounter frequency always become positive. Okay. So, let me write again the expression that omega e is equal to omega, let me go with the second one, v by v omega into cos beta. Now, here if you take that deep water situation or deep water case, where the dispersion relation becomes omega square equal to g into k, right, and then we know that omega by k equal to g by omega. Now, this omega by k is nothing but my v omega over here. So, v omega equal to nothing but g by omega. Now, if I substitute over here, so we can get omega e equal to omega into 1 minus v divided by g by omega into cos of beta, and then finally you can get omega e equal to omega into 1 minus omega by g into v cos beta. Okay. So, for in case of a deep water, we are going to use this relationship, and actually in this course we are really going to use this because we are always dealing with the deep water situation where this dispersive relationship holds. Okay. Now, there are so many discussion is possible over here. Okay, I just tell you only two possibilities. Let us take the two extreme situation when b equal to 180 degree, what is happening. Then you can see my omega e equal to omega into 1 plus omega by g into v, because cos beta equal to minus 1. And if you take this beta equal to 0, so that time you can take omega e equal to omega into 1 minus omega by g into v, because at that time cos 0 it is 1. Now, if you look at these two equation, you can see that omega, the nature of omega is a quadratic, and here it is always positive because this is plus. Now, if I try to draw a graph between, let us take omega e to omega, you can see this is quadratic graph. So, it should be go like this way. Now, here we have one advantage. This advantage as follows, that if we talk about this and this, so for each omega I have one omega e for sure. But now, if you look at this one, now if you try to plot a graph here, it is omega e versus omega, then you can see this graph should be go like this way, and then since it is not negative, I should go like this way. So, both are quadratic, but the nature is different. Now, here the problem is in this following C condition, we can have 3 same omega encounter frequency for different omega 1, omega 2 and omega 3. So, therefore, in case of a following waves, it is really difficult to find out at this, if this is your encounter frequency, what is the corresponding wave frequency, right. This is, I mean, this all discussion it is actually should do in separate sea keeping course. So, we are not going much detail into this. So, we drop this the concept of encounter frequency here, and let us try to discuss the other two concepts, which is the what is the forward speed effect on the kinematic free surface boundary condition. Now, in case of a now here we need to define two reference frame. Now, one reference frame is in Earth's fixed system, and then we can draw another reference frame, let us say, which is let us say on the ship, and which is let us say moving with a velocity u with the ship. So, here I have another reference frame. Now, if I try to write the kinematic free surface boundary condition with this moving reference frame, how do I do that? So, if it is with respect to fixed space, does not matter, but now I need to write the same thing with respect to the moving reference frame. Okay. Now, I know that the kinematic free surface boundary condition it is d dt of z minus eta equal to 0. Now, how I write this ddt is del del t plus u dot grad. Now, here in case of u dot grad, because the reference is itself moving with a velocity. Now, if you do this v vector, the velocity, it is u comma 0 comma 0. So, definitely this equation going to modify it as del del t plus u minus this capital U. Now, or you can say capital V vector dot grad. Now, once I do that, then my kinematic free surface boundary condition become del del t into z minus eta equal to del del t plus u minus v dot grad into z minus eta, and that is going to be equal to 0. Okay. Now, if I do this, then what I get as follows. We are having this del del t into z minus eta plus we have now u minus capital U into del del x into z minus eta plus v into del del y into z minus eta, and then plus w into del del z into z minus eta, and that should be equal to 0. Okay. So, now remaining part is very simple, it is minus del eta del t plus u minus capital U into minus del eta del x, and then plus, or okay, let us take minus. So, then v into del eta del y, and then plus w into plus w equal to 0. So, then I got w equal to del eta del t. Now, here it is minus. So, I can take plus u minus u into del eta del x minus v into del eta del y. So, this is my kinematic free surface boundary condition for the moving frame of reference. Okay. Now, you see the only difference is we are having one extra term, okay, because of this forward speed. Fine. Now, let me write the dynamic free surface boundary condition, and after that today we are going to end this lecture. Now, to write the dynamic free surface boundary condition, you know that it is nothing but del phi del t plus g eta equal to 0. I mean, I am taking the linear only. Okay, let us take the linear case only. Now, here, now we need to understand this is for the fixed reference frame. Now, what should be the moving reference frame? This thing. Now, if we know that this the here the definition is nothing but it is limit of, let us take delta t tending to 0, then phi of x comma t plus delta t minus phi t divided by delta t, something like this, right. So, I am fixing this position and I am taking the displacement of the body, some qualitatively you can see that. But now, what is happening in case of a fixed reference frame, when you try to measure this, the body itself moves some velocity and then the position will shift from here to some other position. So, what is happening with respect to the body fixed coordinate system, thing is what is happening is at it we can think of it is delta t tending to 0, Now, phi actually is the position moves from some delta x and of course, minus phi x comma t divided by delta t. So, something like this is happening. So, this is we can say that del phi del t with respect to the body, something like this is something that is happening. Okay. Now, let us see that how we can relate these two. Okay. So, now let us do the Taylor's expansion of x plus delta x comma t plus delta t equal to, you can say it is phi x comma t plus delta x comma del phi del x and then plus delta t into del phi del t, right. Now, if it is so, now then I just do some mathematical manipulation. I just make this t plus delta t minus phi of x comma t divided. Now, okay, this equals to delta x into del phi del t plus delta t into del phi del t. Now, I divided everything with respect to delta t and taking limit tending to 0. So, I have delta t tending to 0 phi of x plus delta x comma t plus delta t minus phi x comma t divided by delta t, this is equals. So, now it is when you take the limit delta t tending to 0 del x del t into it is del phi del x plus del phi del t. Now, if the limiting position, this becomes my velocity u and this of course, I am getting this del phi del t of body. Now, if I take this side, so minus u into del phi del x equal to del phi del t at fixed. So, therefore, this is the relationship between the fixed frame and then moving frame. So, whenever I write del phi del t for the fixed frame, it is equals to del phi del t on the moving frame minus u into del phi del x. Now, with this knowledge, so now I just replace this dynamic free surface boundary condition is del phi del t plus g eta equal to 0. Now, I am going to write as follows, it is del phi del t minus u into del phi del x plus g eta equal to 0. So, this is going to be my dynamic free surface boundary condition. Now, from here directly actually we can write the linearized free surface boundary condition, which is nothing but. So, now let us try to write the combined free surface boundary condition. Now, how do I write it? Now, from this equation I can modify this as del del t minus u into del del x whole phi plus g eta equal to 0. So, the important part is I can write this one like this way. So, now if you know that the combined free surface boundary condition is phi t t plus g into phi z equal to 0. So, this actually I need to replace by this. So, combined free surface condition with respect to the moving coordinate system is as follows. Right. So, this is the combined the free surface boundary condition that should be applied z equal to 0. So, now here when from the next class onwards we are going to discuss on strip theory, we are going to use this kinematic free surface boundary condition for the moving reference frame. Okay. So, that is all for today. So, we are going to meet next class, we are going to start strip theory from the next class. Okay. Thank you.